Welcome back everyone. So in this video let us work out some examples based on the local maxima and local minima using the discriminant test. Okay, I'll work out this exercises from the Gorpade's exercise section, Gorpade's and Lime's exercise section of the book. Right, you all can work out this, you all can go through the solved examples which are there on the book. I'm doing the unsolved exercises. Okay, so let's start. So first one we'll start with is f of xy is equal to 6x square minus 2x cube plus 3y square plus 6xy. Okay. So the first thing over here is for us to do is to find the critical points. So how to find the critical points? First find the derivatives, first order derivatives. That's going to become 12x minus 6x square plus 6y. Okay, and fy you're going to get it as 6y plus 6x. Okay, so now what do we know at critical point? At critical point, gradient of fx gradient of f at x naught y naught, the critical point is 0. Okay, so let us put fx equal to 0 and fy is equal to 0 and try to simplify. So this one is the easier thing to simplify. So you get 6y plus 6x is equal to 0. This will help you in concluding that y is equal to minus x, right? And the other thing is going to give you this thing gives you 12x minus 6x square plus 6y. This is equal to 0, right? We can cancel a 6 out here. So this is just 2x minus x square plus y. But what do you know about y? Y is equal to minus x, right? So you get 2x minus x square minus x equal to 0. So this will leave you with x minus x square is equal to 0. This one can be simplified as 1 minus x. So this implies that x is equal to 0 or x is equal to 1, right? Now if x is 0, what should be the corresponding y value? Y value will also turn out to be minus of 0, that is 0 only, or here it will become y is equal to minus 1. So what are the critical points you got? 0, 0 and 1, minus 1. Okay, so you have found two critical points. Okay, so having done this, now let us go to the second order derivatives. Okay, this is the end of the first part. So write down over there. Thus 0, 0 and 1 minus 1 are critical points. So here now we are finding the maxima we're finding the local maxima and local minima in the entire domain, that is R2, right? So here we don't have any borders or corner points or something like that which we have to verify it. When we are doing absolute maxima, remember we are checking the maxima on the border also and on the corner points also of that region, right? So for that reason that was a closed and bounded area. This is not a closed and bounded area. This is basically an infinite set R2 which we are working on. So Here there are no borders and all to calculate over here separately. So only find the critical points and classify them as maxima or minima. Nothing else you have to do. Okay, so this is kind of easier compared to the absolute maxima problems. Okay, so now so we are finding the second order derivatives. Second order derivatives over there, we had about 12x minus 6x square plus 6y, right? So second order derivative of that will become 12 minus 12x plus 0 it will be, and fy that will become 6, and fx y will also turn out to be 6. So write down the Hessian matrix because it will be easier for you to remember. Yeah, so when I say Hessian, write down Hessian at a point. Okay, Hessian at 0, 0 will be what? It will become 12 minus 0. Yeah, if you want to write them down manually first. fxx at 0, 0, this is going to be 12, and fyy at 0, 0 is also 6, and fxy equal to 6. Okay, so write these entries over here. So this is going to become 12, 6, 6, 6. Okay, clearly you can see that this determinant of this is going to be that delta value. That delta is this 12 into 6 minus 6 square. Okay, this is going to be 36. It's actually 72 minus 36, and that's going to be 36, which is positive, right? So the moment is positive, then only we can think about looking for maxima or minima, right? This is done, and then next you know that fx6 is also positive. Okay, so this 0, 0 is a point of minimum. Okay, this is a point of minimum over here. As I told you, if fxx is positive, fyy will also be positive. That you can see from this example actually. Okay, but examples cannot be used to justify. I'm just saying you can see it in this example. Okay, explanation I've given you. They cannot have opposite signs because that will affect the thing from delta being positive. If fxx and fyy have opposite signs. Okay, so this point is done. Now the next point at 1, minus 1. At 1, minus 1, what is fx6? It will become 12 minus 12. This are constant, they are not affected at which point we talk about them. This quantity turns out to be 0. So Hessian over here is 0, 6, 6, 6 over here, right? So the Hessian turns out to be negative. It turns out to be not Hessian is not negative. The determinant of the Hessian is negative, or the principal minor over here is negative. So this delta value, which is going to be 0 into is 36, which is minus 36, which is less than 0. Okay, so this is second order is not positive. Sorry, if this second order principal minor is not positive, then we say it's going to be a saddle point. Okay, this is a saddle point. So this is done. Let's try out one more example. Next example over here. This is example number 5 on the book in the exercises. So fxy is equal to x cube plus y cube minus 3x minus 3xy plus 15. Fx, the first order partial derivative over here is 3x square minus 3y. Fy minus 3x. Okay. Yeah, since we are already in the mood of taking derivatives, why don't we find the second order also straight away? Fxx is going to be 6x, Fy 6y, and Fxy, or Fyx also for that matter, both of them are equal to 3. Okay. What remains for us is only to find the critical points. Okay, so at the critical points, gradient of f is equal to 0, 0. Okay, so this implies that fx equal to 3x squared not square, this you put it equal to 0, and fy this is going to become equal to 3y minus 3x, this is equal to 0. So here you are going to conclude that x square is equal to y, and here you are going to conclude that y square is equal to x, right? So substitute one equation into the other. See, at the critical point, both these people have to be 0 simultaneously, right? So you can substitute one of the expressions into the other expression. Okay, it's not that you solve them separately and get two different answers. Yeah, so x is equal to y square, right? So what will substitute where? Y square is equal to x. Okay, so x is equal to y square, that's what we know here, and x square becomes y. So this will become, just write this as y square is equal to y raised to 4 minus y is equal to 0. So this will imply that y into y cube minus y, this is equal to 0. So this implies that y is equal to 0 and or y cube is equal to 1, right? But whose cube becomes 1? Only plus 1 gives you cube as 1, right? Minus 1 gives you cube as minus 1. Okay, so this will imply that y is equal to 1. Minus 1 will not give you plus 1 as a cube. Okay. So here we have these 2 points. So now we'll try to find x. So the relation is x square is equal to y, right? Oh, we'll use this one, y square is equal to x. Okay, so 0 square so this will imply that x is equal to 0. Then we'll see 0 again. then you know y is equal to 1, right? So 1 square is equal to x. It will be 1, and this will imply that x is also equal to 1. Okay. So what are the points we get? Hence 0, 0 and 1, 1 are critical points. Okay, we have already calculated the other things. Now let us work out the behavior at each of these points. Okay, so first to start with, at 0, 0. What is going to be fx6 at 0, 0? It's 6x actually, right? So that will turn out to be 0. F5y is equal to 6y, that will be 0. And fxy, that is equal to minus 3, so it will remain minus 3. That Hessian matrix of yours now will become this, minus 3, minus 3. Clearly, you can see its determinant is, determinant of this delta is equal to minus 9, which is negative, right? So it's a saddle point. Okay, 0, 0 is a saddle point. Okay, next at 1, 1, what will get here? At 1, 1, fx6 becomes 6, fyy also becomes 6, right? So we'll get 6, 6 minus 3, minus 3. Okay, 6, 6, this will become 36, minus 9, that's equal to 27, which is positive, right? And also fx6 is also positive, right? Similarly, fyy is also positive, but we are just considering one of them. Okay. If, as I explained to you all in the previous video, if one of them is positive, the other one also has to be positive. If one is negative, other one also has to be negative. Okay. If one is 0, then most likely you're going to end up with a saddle point. Okay. Yeah, you actually are going to end up with a saddle point, not most likely. Okay. So this fx, yeah. So 1, 1 is a point of minima. Okay, sorry, you should be specific. Local minima. Okay, same one of the previous one also write that down. Saddle is saddle anyways. Nothing called a local saddle. Where is this previous one? This is also minima. Okay, we have dealt with only minima so far. I thought this was maxima. Okay, so this is also local minima. Okay. Okay, so moving on to the next problem. In this way. So third one, which is actually the third one in the book also. So 1 to 3 fxy x square minus y square. Yeah, so let us work this out. This will become 2x, fy is going to become minus 2y. Okay, and yeah, fxx, if you don't like, you can calculate this later on. It's not compulsory to calculate the double derivatives at this stage only. And fxy, this is going to become 0, right? Yeah, so clearly if gradient is equal to 0, this will imply that x is equal to 0 and y is equal to 0. Okay, so thus 0 0 is the only critical point. Okay, is the only critical point. Now let us check what is going to be the behavior of the Hessian. So 0 0 minus 2. Okay, so as I told you all, both these people should have been sharing the same sign, right? But here they are sharing opposite signs. So what will happen? Obviously the determinant will turn out to be negative. Okay, the second order determinant is negative, and hence this is a 0 0 is a saddle point. Okay, 0 0 is a saddle point. So this is what we get. Okay, so these are all the examples which I had to do. There are some couple of more examples, but that I will not be able to do now. Yeah, but one more thing, just keep in mind over here. Okay, just keep one thing in mind over here is that this is not a universal method. Okay, not that every problem which you get in the world can be solved. You can find its local maxima, local minima using this method. There are certain functions where the discriminant test fails. Okay, the discriminant test fails, that you get the see what I have told you what to do when the Hessian is positive. You'll get either a maxima or minima, and if the Hessian is negative, the determinant of the Hessian, if determinant of the Hessian turns out to be positive, it will either be maxima or minima depending on fxx or fyy value, right? And if Hessian is negative, determinant of Hessian is negative, it will turn out to be a saddle point. But what if the determinant turns out to be 0? We have not handled that case, right? So that case is there, and that's the place where this discriminant test fails. Okay, so those problems you have to manually verify whether it's a maxima or minima. Okay, so right now I don't have an example on that, but anyways we'll see later about that. Okay, so that's all for this video. Thank you for watching. Bye bye.